thanks everyone for having me here today. So today I'm going to talk about our my joint work with Ignacio Cascudo, he's my advisor, on IOPs for Boolean R1CS statements. So our work in a nutshell, essentially the most significant bits of this presentation is going to be the following two lines. So essentially what we do is just that we build a more efficient SNARK for R1CS over F2, starting from already constructed SNARKs for R1CS over FQ. Now, as you can see, there is a lot of jargons in this sentence, and I don't assume actually much background in applied cryptography, like, for instance, what are SNARKs or what R1CS are. So the main goal of this presentation is going to make all of those acronyms meaningful, and hopefully also our results interesting at the end. So I'm going to tell you what is a SNARK. That is essentially a primitive introduced recently in cryptography. That in the last years I've seen there's been a lot of interest around these objects recently. What is an R1CS? That is essentially a more mathematical object. So that's also where the coding theory comes. So next, I'm going to tell you why the Boolean case is interesting, giving a few examples of applied scenarios, why Boolean circuits comes into play and why they're interesting and why they're applied. And finally, I will briefly mention how do we get to produce more efficient constructions. So to begin with, let me introduce what a SNARK is. So for those of you who are familiar with interactive proofs, a SNARK is essentially an interactive proof. It's an interactive proof with a set of constraints. First of all, SNARKs has to prove a relationship that has to be NP complete. And second, it has to be non-interactive and succinct, meaning that even if the input is extremely large, the communication between prover and verifier has to be extremely short, usually polylogarithmic or constant. So the most used NP complete relation in this case in those cases is usually circuit satisfiability, meaning that there is a prover and a verifier. They both have a circuit, and only the prover essentially holds a vector W that evaluates the circuit to 1, for example. What we want to do is essentially to make the prover and verifier communicates and convince the verifier that there actually exists a point W and that evaluates the circuit to 1. Okay. So this, of course, is non-trivial. I mean, they're given a certain circuits, which essentially you can think as a graph where each nodes contain a multiplication or addition gates. Or if you prefer a more algebraic interpretation of these objects, you can simply think of an hypersurfaces over some space. Actually, this hypersurface can have no points, especially since we usually consider finite fields. So this relationship is non-trivial, and actually, as I said before, is NP complete. Okay. So just to make it more explicit, so as I said before, essentially this is a non-interactive proof, but still a proof system. So there is a prover and a verifier. The prover holds the secret W. This is the point in which the circuit evaluates to 1. And essentially giving this proof to the verifier, we want the verifier to either accept or reject the proof. And the verifier should only accept if the point...
I'm sorry, Emanuele, I just can't answer a question.
Yeah, sure.
What is exactly an NP complete relation?
Sure. I should go back. So essentially, so I just assume, okay, I'm not even assuming NP. So NP is a language essentially. And by language, I mean a set of strings essentially, such that we don't know if this language is desirable. So we don't know if an input, an element is given any string, if we can decide if the strings belongs or not to the language. So for instance, if I give you a circuit, we don't know if it's easy or not to determine if there is a point W that makes the circuit evaluates to 1.
Okay.
Even though the class NP determines all the strings essentially, and the languages, such that there is always an int, in this case the point w, that makes us decide in polynomial time if the circuit is satisfiable or not. And by complete, in this case, I mean that any MP language, if you can solve decidability for this language, we can solve decidability for any other MP language. An instance, for instance, an example could be maybe Hamiltonian cycle. If we can solve this problem, we can also solve Hamiltonian cycles or any other MP language.
No, okay, but it's okay for me, the concept of NP complete as a class of problem. It was the relation.
Sorry, yeah, okay, that's the point. Okay, no, so of course, usually they're defined by relation because essentially to link the instance and the witness, but the language is defined as the element C such that there exists a witness W.
Yeah, yeah.
Okay, sorry. Okay, I thought it was more general question.
After your, thank you.
Okay, sorry. Okay, so okay, that's essentially what a SNARKs is. Now the next point is to define what is an R1CS. Now, an arithmetic circuit essentially doesn't have doesn't have a nice algebraic structure. It's often very hard to work with them, especially when you're trying to prove that they are satisfiable. So essentially, a characterization of those circuits, or better, a transformation of those circuits, has been applied in the recent years in order to build easier proofs. And the idea is to move from a circuit that essentially represents, as shown below, essentially just an hypersurface. The idea is to add to this hypersurface extra variables and to consider, instead of just an hypersurface, a set of constraints that are only quadratic. So in the end, we can express the whole constraint that before as maybe higher degree into a set of constraints of only degree 2. As expressed above. So here we have only the first two terms that essentially is a quadratic term. By the way, sorry, with the asterisk, here I mean essentially the component-wise or Hadamard products, if you prefer. And of course, the light blue part is essentially linear terms that appear, for instance, in the example below as the term t. And finally, there is a constant term, which is also important because we want eventually the whole circuit to evaluate to 1. Okay. So, moving on, how are R1CS easier to deal with? Why are they easier to deal with, and how are they essentially used? So the main idea is once we have an R1CS, essentially a system as expressed before over a finite field, the idea is that we can complicate things even more and introduce more extra variables in order to linearize the problem. Essentially, we can introduce 3 extra vector, x1, x2, x3, essentially accounting for these 3 terms, a1, a2, and then 3 times w. That is our witness. And what we have to show is that there exists x1, x2, and x3, and a vector w that satisfy this 4 vector condition, linear condition. I mean, the first 3 are linear and the last one is quadratic. So at this point, this is exactly where linear codes finally comes into play, because most of the systems that are currently used in order to achieve also succinct communication deploy linear codes, because essentially if a prover knows W and consequently also x1, x2, and x3, he can encode through, for instance, a Reed-Solomon code, these vectors, and together with some randomness, of course, in order to avoid disclosing any sensitive information. And subsequently, the verifier can ask to open these code words that the prover committed at first in specific position, specific indexes. And instead of just opening, for instance, a code word, the verifier can ask to open a linear combination or even more, even product of these code words. For instance, in the last case, given code words f1, f2, and f3 for the vector x1, x2, and x3, we can ask to open a single position of the product of the first 2 and check if this is equal to, in a given position, to the code word associated to x3 plus a code word associated to b, which the verifier can compute on its own. So that's essentially how to prove things, but this also implies that there is, I imply a huge issue, meaning essentially the fact that Reed-Solomon code implies that the field f has to be large enough. So the issue comes when the field has to be large, but we want to prove statements that are intrinsically Boolean. And the two most important examples that comes to mind are essentially when we want to show that, for instance, we know the preimage of an hash function, which is also where we would like to use SNARKs, because those are usually problems where there is not enough algebraic structure, and we really need to show that the circuits evaluate that we know the upper image of a given circuit. And this is the first example. And the second one instead is given a symmetric encryption scheme to know that either the plain text or a property satisfied by the plain text. For instance, if you are doing maybe, I don't know, electronic voting, we would like to show that the plain text, for instance, is either one of the candidates, or other examples may come to mind. So this is actually not an issue in general, to the strategy I outlined before. Even if the field has to be large, indeed, we can essentially embed F2 over a larger field, especially if this larger field is actually, essentially, if the size of the larger field is essentially a power of 2. We can essentially think, okay, F2 as a subset of this larger field, and then embeds this statement, interpret this statement again over FQ. The only issue, though, is that we need to add extra constraints. In this case, we need to enforce that every variables wj satisfy the constraints wj squared minus wj is equal to 0, meaning essentially that wj is either 1 or 0. And this is necessary because otherwise constraints that before were unsatisfiable might become satisfiable over a larger field. I mean, a trivial example could be x squared plus x equal to 1, which is clearly unsatisfiable over F2, but becomes satisfiable over F4. Okay, this approach is actually, it works. It has been actually deployed in several systems, even concrete systems, but it's significantly wasteful because for each bits of witness, we're essentially using log Q bits in the proof. Meaning, okay, just to give you a scale of how this works, log Q usually is around 128. So we expect to actually have a significant overhead in our final construction using these kind of embeddings. So what we can do is to find better embeddings to achieve essentially better embeddings to overcome this issue of embedding directly F2 to the larger field. So what do we use is a reverse multiplication friendly embedding. Now, this tool essentially comes from algebraic geometric codes, and or even Reed-Solomon, but in a specific case, though. And essentially, there are a pair of linear maps that allow us to encode k bits in a larger field of dimension E. So hopefully, k is larger than 1. That's what we are aiming to achieve. And especially the larger rates, the lower the rates e to the k, e over k, the better the embedding it is. And the nice property of this embedding is that it allows us to compute essentially the Hadamard products of two embedded vectors. So given the embedding of x and y, we have another maps that goes back to f2 to the k that allow us to compute essentially the Hadamard products of x and y. So there is a theorem, essentially by Cascudo, Kramer, Shin, and Yuan from 2018 that shows that from algebraic codes, essentially coming from towers of asymptotically good algebraic function fields with a lot of rational points, these embeddings can achieve rates around 5. Even though for smaller parameters that are essentially the one used in practice, we can even get better rates across 3 and 4. Okay, so next question is, how do we use an RMFE to essentially solve the problem we want to show, essentially R1CS? So the first step is to show how to use an RMFE to compute an inner product. So before, I've told you that an RMFE essentially allows us to compute easily the Hadamard product of two vectors, even after we encode. So in order to compute the scalar product, the basic idea is just to consider another linear map, the map S that I've called here, that goes from F2 to the K to F2 simply. And that takes a vector and simply returns the sum of all its components. And essentially, the basic idea is that given two encodings, we can multiply them and apply psi. Applying psi, we get the Hadamard product of these two vectors, and summing, of course, we get the inner product. So in order to state this relation just in the larger field, because remember that the only tools we have are essentially the ones that were previously built in other construction over the larger field. So this statement becomes something like the embedding of x times the embedding of y has to lie in the kernel of S composed with psi. By the way, I stress here that the larger field is clearly seen in this case as an F2 vector space, and psi and S are both F2 linear maps. So in this case, it's meaningful to denote the set of zeros of these two maps as a kernel. So next is how to move from just showing that an inner product is zero to show that actually a linear equation is zero. And the idea is here simply that a linear equation is nothing more than a set of inner products, several actually inner products at the same time. So what do we do is essentially to see the matrix A as a set of row vectors, and encode each of these rows. And of course, we also encode the element X, which is going to be our witness essentially. And in order to show that the system on the left is equal to zero, we just show that the system on the right, which I stress here now as entries in the larger field, lies exactly in the kernel of S composed with psi. Okay, so just to build a bit of notation, the embeddings, the embedded matrix that appears on the right-hand side, I will call it A tilde. And this is going to be useful in the next slides. So we are now ready. Now we can finally fully characterize the R1CS over a larger field using an RMFE. And essentially, using an RMFE. So, okay, this might look scary, but actually is essentially what I've been telling so far. So what we would like to do is essentially given an R1CS here, A1, A2, and A3, all lying over a Boolean field, F2. Calling X1, X2, and X3 the products of A1, A2, and A3 with W. We can encode these elements, X and Y, using our embedding phi. Encoding our elements results in new vectors X, Y, X2, X3 tilde, and W tilde. And what we want to show is that these encodings essentially lies in the image of phi. Essentially, those vectors that we are producing are were embedded correctly. We want to show the second to last constraint essentially is what I've shown before, what I've told before. Essentially, this kind of constraint embed using the RMFE. So this essentially is equivalent to show that AI times W is equal to X. And finally, there is a tiny little trick here. So I think I need to go back to how R1CS was defined. Sorry for this little jump. Essentially, there is the last quadratic constraint here. X1 times X2 is equal to X3 plus B. The idea is that if we encode X1 and X2, we can easily recover using psi the Hadamard product of these two. So I'll go back. So the Hadamard product here is essentially the values that T contains. And what we want to show is essentially that the Hadamard product of X1 and X2 is equal to X3 plus B, where we use this tiny little trick here that we can essentially recover X from its encoding, essentially by multiplying by this element 2. Okay. So this is essentially an R1CS that now, that now is defined over the larger field. The only trick, though, which I'm not going to explain furthermore because of just to stay within the time limits, is that here I'm not exactly using equation, but equation modulo a vector space over the larger field. So in our paper, we actually address this issue, defining a generalization of what is essentially a link check, essentially a test that essentially checks if a linear relationship is true. In our case, we generalize it to check if this relationship is true, modulo a vector space that is given. So up to having that extra tool that I haven't explained, one can easily then transform SNARKs that works over larger fields to SNARKs that now works essentially over F2. So since this talk is actually a little bit more applied, we also made comparison with previous works. I stress again, only in the case of Boolean constraints, set of constraints, essentially Boolean R1CS. And in this case, we compare with several works. Actually, there are many more SNARKs, and we cannot really apply our technique to all of them, but those are the ones that we can really apply our technique to. We essentially show that the proof size in the end becomes significantly smaller in one case, essentially the case of Ligero. And in other case of SNARKs that are polylogarithmic, it becomes small enough to, significant, not really significant, but its proof size is reduced by a measurable amount of kilobytes. So that's essentially all, and I really thank you for your attention.